Because I write the WebAudio API, but like the most interesting thing I do with it is the unit tests, so it's not great. And on the other hand, I do music, and I started to make music with the WebAudio API. So we're going to look into how we can do it and go through a journey of maps and sound and old synthesizer and stuff like that. So today we're going to start with a very bold item, what is music, and try to narrow the scope down a bit, because I think it's just a 1 hour talk, and yeah. And then we're going to deconstruct an acid techno track, and we'll determine why we picked acid techno in the first place. Then we're going to talk about what would you want to do rich audio on the web anyway. And then a little Web Audio 101, Web Audio primer, what it is about, how it works, what is the model, what can we do with it. And then we're going to try to code something live and to make a techno track right in the text editor from scratch. I mean, 90% from scratch. I've pre-coded some stuff, but and then it might work. So yeah, there's going to be some sound, and it's going to break horribly, but that's okay. And then we can dance item 8 here. Yeah. So yeah, so what is music? I picked a very simplistic definition because we don't have a lot of time. So music is rhythm, melody, and timbre, right? So rhythm is just at a particular point of time, do you have a sound or you have silence? And then from this definition, you can build like quarter notes and eighths and sixths and everything. But yeah, really, it's like at a point in time, is there some sound or not? It can be organized, it can be disorganized. Yeah. A melody is just, you take some phrase and you've got some pitches, and then it's something you can remember distinctively in the tune. And then the last one, we talk about the very intrinsic characteristic of an instrument, whether it's a violin, it's a guitar, it's a piano. You can really recognize what it is because of this characteristic. And today we're going to mostly focus on this last characteristic of the sound, because scheduling sound happening in a web browser is not the most interesting topic, but learning how to make a very cool bass sound, I mean, yeah, I think we agree. So acid techno, it's a genre of music that appeared in 1990, and there is no sound. Why is there no sound? I don't know. I mean, if there is no sound, we can just all go home, because this talk is not very interesting. All right. Let's try it again. Whoop. Still no sounds. My volume is up. Can we do something about it? Just going to wait patiently for the tech people. Have some water.
They told me really to just plug in.
What?
They just told me to plug in.
Right. Whoops. Oops. Ah, yeah, cool. Techno. Okay, so acid techno. So yeah, it's techno. So in this excerpt, you found specifically 2 machines, and they used only 2 machines, and they are completely analog. So we've got the TB303 bass synth, which is pretty cool. It used to be super cheap. Now it's like $3,000 because everybody wants one, and they are not made anymore. And the second one is a drum machine, TR-808, very expensive as well. Used to be super cheap. So when we heard this tune, right? So in this tune we have a kick drum, right? A maracas sound, right? We have a clap. So if we go full on the drums, and then we have just a bass line. You can see it changes over time a bit. And then we mix everything. Pretty standard electronic music setup, a percussion and a bass. We're good. Why would we do that in the first place, though? It sounds good. I'm a techno fan, so I get what, like, I'm on stage, I decide. So it sounds good, but more importantly, in a talk, it's very easy to code, as we will see. So we're going to do a kick drum, we're going to do a clap and a maracas. We're going to all simulate that in code, live. And that's going to be easy, and you will all understand. And then the bass line, we're going to simulate a very cheap version of the 303, but it sounds all right, so it's just fine. So to do all that and to make sound, we're going to use the Web Audio API. The Web Audio API is, and I quote the specification, describes a high-level JavaScript API for processing and synthesizing audio in web applications. So we don't say web pages anymore, because it's not cool. We say web applications because we can do anything with it, including acid techno. So then it goes on. The paradigm is an audio routing graph, and you will have an image, so you can understand what it is all about. You have a number of audio node objects, and you connect them together to make some sound or to process some sound. Right. And you don't code the algorithm in JavaScript. You just use predefined blocks of logic that you connect together to form a synth. But you can also do it manually in JavaScript if you feel like it. But we won't do that today. But why? Why would you do that in JavaScript? Because JavaScript is supposed to be terrible. Everybody hates it. I mean, not me. I'm from Mozilla, so, you know, it's kind of my job. But I've isolated 4 characteristics where the Web Audio API is simply much better than a lot of the alternatives when it comes to making music. First is distribution mechanism, then performance, ease of use, and composability. So we'll explore that. Distribution mechanism simply means you want to distribute your audio experiment. You give someone a URL, they can click on it, and it's done. Nothing else has to be done. So they click, and sound happens, and then everybody's happy. They don't have to install your Ableton Live or Max MSP or Pure Data or anything. It just works. And it works in any modern browser, Chrome, Firefox, Safari, IE even. So you're good. Performance. We have optimized the crap out of everything, to be very blunt about it. It took a long time, but now everything runs super smoothly. You can have tons and tons and tons and tons of audio coming on, a lot of processing, massive reverbs, everything. So you can just do massive stuff. There has been like symphonic orchestra rendering in the Web Audio API, so at this point, you're good. Ease of use. From 0 to acid techno, it takes 25 minutes. So very, very easy. If you've got, if you know what a sine wave is, then you know a lot more than what is necessary to actually have fun with it. And composability means you can use it as part of a bigger system. For example, if you do a voice over IP application using WebRTC, you can use WebAudio API to process your sound, or you can make it work with the recorder API or the get user media API to use your microphone. You can connect, mix and match with a number of other APIs. For example, WebGL if you want to do 3D rendering, or a Canvas if you want to do 2D rendering, or like even the DOM if you want a massive number of sliders to control each of your parameters. And this is very powerful because a lot of people know how the web works. So now you've got audio on top of that. And yeah, so the web is not just for writing web pages anymore, as I was saying before. There's been AAA video games written for the web. There's been like everything. So here is just a number of things. Oh yeah, there's so much things written with it that goes out of the slide. Anyway, so yeah, randomly video games, interactive art installation, electrocardiogram filtering software. Like you can do anything and everything. Phone keypad, when the little sound it does when you push on a normal phone. VR, music playback software. Yeah, so yeah, you can do really anything. It's very powerful, and if it's not powerful enough, we'll keep adding new features. So you know. So okay, now we know why we want to do that. So we need the tools and to know what to type in text editor to go there, to make acid techno and to be super high on the charts. So WebAudio API, the three main concepts: audio context, audio nodes, audio params, right? It starts with audio all the time. So to get an audio context, very easy. var AC equals new audio context. This does a number of stuff internally, but basically is the object from where you get everything else. You will get all your other objects and call all your methods from this one audio context. Then the goal is to do a rendering graph. So for example, you can have an oscillator that makes a square wave or a sine wave or something like that. You can connect it to a gain node, and when the output of the sine wave comes and gets processed by this other node. And maybe you want to filter it, so you connect it to a filter. And maybe you want to have a reverb, so connect it to reverb. And then when you're satisfied with your rendering, you can connect it to the destination node. And whenever you connect something to the destination node, you hear it in your speakers. So that's good, right? So a very easy concept. So what can you do? Oh, it's too big. Eesh. Yeah. Okay, so the audio context, I outlined a number of methods that you can have. You have the destination. Yep.
When you turned on, it switched to 1024 by
I think it should be.
4 by 3 now.
Yeah, I can just zoom down. Thank you. So yeah, on the audio context, you have the destination. You connect everything to the destination. You have the current time. It's a time that increases all the time and represents where you're at. So you want to use, if you want to schedule something in the future, you can say current time plus 3 seconds, and this means 3 seconds in the future. It's always increasing. You cannot really pause it, play it, rewind it. It's just going, it's just a monotonous clock. Then you can create a number of nodes which you will connect to make your graph. For example, a buffer source is something you use to play back a sample, just a short audio excerpt. A gain is something you use to change the volume of incoming audio. An oscillator lets you create very simple waveforms, like a square, a triangle, a sawtooth, a sine wave, something like that. Very mathematical. And a backward filter, we will see in the future, lets you alter the characteristic of the sound, the sonic properties of it. The oscillator node, for example, we will use it a lot in the rest of the talk. You can connect it to another node. So this means the output of the oscillator node will get processed by the node you connect it to. Well, it can be any node, really. You can, of course, disconnect it if you want to change the shape of the graph. You can alter the frequency of the oscillation. To have a very high-pitched sound, you have a high frequency. A low-pitched sound, you have a very low frequency. You can detune it, that is, slightly change its frequency relative to a base frequency. We will see how useful it is in just a few minutes. And you can change the type. For example, a sine wave, square wave, sawtooth, triangle. It's just a string. You say type equals triangle. It makes you a triangle. Everything is fine. You can start it and stop it at a very specific time. So this is self-explanatory, really. When you start it, it starts outputting the wave. When you stop it, it stops. Very easy. And then you have audio params. You have noticed that the three attributes in the middle are audio params. No, the two in the middle. And audio params is very useful because they have a value, of course. For example, the frequency could be 440 hertz, which is a A4. But if you want to have a very smooth ramp with a very specific shape, an exponential shape, then you don't have to set it very fast in a loop. You can say, oh, okay, so from now until 3 seconds later, do a nice curve with an exponential shape with this constant. And it will do it for you, and you don't have to do anything. So this is very useful. For example, like we have the current time in X, and you have the value in Y. So for example, at time 1.0, I set it to 1.0, and then I do it to do a ramp to 0, and I want the ramp to finish at 2 seconds. And then I want to have it 1.3, and then I want to decrease. So I just do 4 audio param calls, and it makes the shape, and then I can just lay back, and it will do it for me. So we will use audio param extensively in just a minute. So now, demo time. So first, we create an oscillator. In all the demos, we have AC, which is the audio context. So I don't want it to be repeated on each slide. But so AC create oscillator. So we get ourselves an oscillator. We get a gain. The gain again lets you change the volume of what is coming into it. And then we set the type to a sine wave. We set the value to 440. And then we get ourselves 2 sliders to change the value of the gain here and the frequency here. We'll see the 2 sliders in a second. And then you connect the oscillator to the gain and the gain to the destination. So you should hear a sine wave with a volume. So, whoop. You can change here. Oh, my sliders are out of the, oops, okay. You can change the height, the pitch of the sound, and the volume of it. And you see it's just a sine wave, but the frequency of it changes. I can make, similarly, a square wave. It sounds much more harsh. And a triangle, very smooth. And a sawtooth. Okay. So this is the basic tools we're going to use today to create techno, nothing else. So now, having a very static sound is not very great. It's super boring, in fact. So what we can do is to use an audio param to automatically 400 per second, make the sound decrease, create a little percussive sound. So we have something like that. Starts like a big drum you hit. And the waveform is actual waveform. It's not like cheating. It's exactly what is coming out of the speakers. Okay. So we see to do that, we set value at time now, current time, to 1.0, which is full volume. And then we decide to do an exponential curve. This is the method to do an exponential curve to 0, which is silence, from current time. And we let it decrease with a constant of 0.3, which is an exponential constant, like in math or physics. So what can we do? We can also do a kick drum, which is the big drum that drummers have, they have with a foot. We can alter the pitch of the sound and the volume of the sound at the same time, which makes it a bit more convincing. Right, so very simple, like a big percussive sound. Okay, so for percussions, we're good. Now we can do a bit things that are more interesting. So let us get 2 oscillators, set it both to sawtooth, let them have the same frequency, and let us change the detune. The detune lets offset a frequency compared to the other. So they will have approximately the same frequency, but not quite. So you will hear what we call the beating effect, where they will phase in and out with themselves, which makes it very interesting. And then, of course, as usual, we connect everything together and start the oscillators. So this is detune. This is detune at 0, so it's not detuned. When it's slightly off, you see this interesting effect. So yeah, again, very simple. Just a couple lines of code in the WebAudio API. Then we need to talk about a very big beast, the frequency domain. So the frequency domain is a different way of representing audio or signal for what it's worth. Instead of having the time in X and the value in Y, you have the height of the sound in X and the volume in Y. So for example, a sine wave is just something like that. So just one spike. Whoops. I need my slider. So yeah, a sine wave is just one spike like that. It moves. A much more rich sound, like a square, is a number of frequencies like that. But what if we want to change exactly the shape of those, what we call harmonics? Then we introduced a filter. So we get the exact same setup as before with the bass, 2 sawtooth. And we add a filter. So the filter has a frequency. Beneath it, higher than this frequency, it stops cutting some sound. Below this frequency, it lets the sound go through. Whoops. This is not ideal. So we have much more high end, much more treble. So we can do things to change the sound we have. Then other tricks we can use, very simple again. We can just use random numbers using math.random, which is a standard JavaScript thing. And if you play back noise, you get noise. Just like when you've got the TV on the wrong channel. I think it doesn't make that anymore, does it? Anyway, yeah. So yeah, just noise, very simple, very useful tool in synthesis. And because clap is a bit more complicated, we cheat and we just get a file like clap.og, download it, and play it back. And it makes a clap sound. But yeah. So this is an actual clap from the 808 that I sampled. So yeah, we're good. Time to alt-tab to a text editor and try to make some sound. Twitter, no, hello. Okay, so, all right, let me get my setup right. So let me just explain in short what we have here. So this is a little HTML page. It's 150 lines long. I've written the boring code. That's like the interesting stuff we're going to write together. So this is a score, kind of a score. So for example, we have a kick here. The kick goes, when there is a 1, it's supposed to hit, and when there is a 0, it stays silent. And whenever there is a 1 here, it kicks again. So we see that we have a very regular pattern here. Whoops. We have 1s here on the first beat, and here, very regular. We see that the hi-hats, which is a little symbol on the left of the drummer usually, it's the opposite. It's called offbeat. So it goes boom, chick, boom, chick, boom, chick. And then we have the clap. Every 2 beats, we're going to hear a clap sound, very acid techno-y. And then we've got a little bass theme. So the numbers is what is a standard called the MIDI notation, so MIDI notes. And you can translate those numbers to a frequency in hertz using this formula that you find in Wikipedia. So it's a bit barbaric, but you know. And then I prepared a number of things. For example, a noise buffer here. This just takes a buffer, fill it with random values. We can play it back later. We have things to know which time we are in terms of musical beat and not in seconds, because in musical beats it's much better to do synchronizations with, for example, your visual artist or something like that. Then we can start the music. And then this very bizarre piece of code is just a piece of code that runs through the score and tells the instrument when to play and when not to play. It is not very interesting. The code is, of course, open source and online, so if you feel like reading it, there's going to be a link at the end with very detailed explanations. So I'm just going to fold that here. And then we have 4 functions. Those 4 functions are going to be called whenever the instrument needs to sound. For example, kick. When the kick has to play, this kick function is going to be called, and we have to fill in the blank and to make it do some sound. And then, of course, loading code to load the clap sound, because we're going to cheat for the clap sound. And yeah, not very interesting. Let me close that. So, to do a classic kick sound, what do we want? We want first an oscillator, because the kick sound is just a big sine wave, in fact. And then you want to change the volume of it with the time. So you want a gain node. So you connect your oscillator to the gain, and you connect the gain to the destination. I've just used a shorthand. Sync is the classic audio term. So this dot sync is the destination for us. Then what do we want? When the note has to start, we want the oscillator to be at full volume. So we set the value at time 1.0. 1.0 is the volume at time t. We see that in this function here, we get the time here. So at time t, we set it to 1.0. And then we want to let it decrease, let it fall off to 0, which is complete silence, from time t with a curve of 0.25, let's say. And then, of course, we want to start our oscillator at time t. And then we're going to stop it sometime later. It's shorter than 1 second anyway, so I'm just going to stop it 1 second later. Okay, does that sound good? No, it doesn't, because we have forgotten to change the pitch of the bass drum, the kick drum. The kick drum is very low end, with a lot of bass, so we need to make it do that. So we change the frequency here, set value at time. Let's say it starts at 50 hertz at time t, and then it drops to 40 hertz. Okay. Maybe we can so this is the page. This is the page in Firefox, and this is my text editor. So, okay. So we've got some sound. Just a bass drum for now. Some variations. Okay, good. My mouse. Yeah. Okay, cool. What would be better is to have a bit more of an attack, like a more bite in the sound. So what could we do? We could use a little square wave to give it a bit more attack. So let us get another oscillator, osc2 type, and we really don't care about the frequency, but let's put it to 40 hertz, the same kind of. And we want to connect it in the same way. Up here, and we don't care about its frequency. We just set it to something fixed. But we changed its volume. We want to make it very short because it's just going to be the moment the beater hits the skin of the drum head, as we call it. Okay, so very short. What does it do? And then we're going to start the oscillator. Okay. Gain 2 here. Oops. Where is my? Yeah. Okay. Cool. It's got a bit more attack. All right. Let's stop that. Now, where we are at, hats, hi-hats. So hi-hats is the little double cymbals you got on the left of a drummer. Makes a very noisy sound, very short but very high-pitched. So what can we do to make a hi-hat? We can get the noise buffer we had before here, And then we set the buffer to the noise buffer function here. So noise buffer just outputs random numbers between -1 and 1, which is the limit you want in audio. So yeah, it's just a Gaussian noise, if you know what that is. So then we want it to be very short, so we need a gain. And we also want it to remove the low frequency of the noise, because the noise is across all frequencies, medium, bass, treble. So what we could do is to create a special type of filter, which is called a high-pass filter. It's called like that because it lets the high pass, it's a high-pass filter. The low-pass filter lets the low pass. So yeah, very easy to remember. Create B-quad filter, and we set its type to high-pass. And we set it to a mostly random value or hand-picked value of 8,000, which sounds good to me. I'm not too sure why. And then we want exactly the same code as for the kick drum. We start it when it is time to start it at 1.0, and we stop it, set target at time. Those functions are really long to type, but we let it drop to silence. It's pretty short, 0.03. And then we connect all this little world together. You can chain the calls, it's pretty cool. Okay, and then you start. So what is gonna happen here is gonna happen that I missed. Where is it? Aha, yeah, cool, thank you. Oops, I'm out. Oh. Yeah, no. So you see a little symbol. Okay, let's stop that. Onwards. For the clap, we're going to just cheat because we've preloaded the sample. So we just want to play it. To play back something in a WebAudio API, you do create a buffer source, create buffer source. The names are really long, but sometimes it's better to have long and descriptive names than names you really don't understand. Create gain. You always use a ton of gain nodes in the WebAudio API because you want to control the volume of everything. Some stuff in the musical performance need to be more in your face than some background sounds sometimes. So now we set the buffer, we've preloaded, and start it. We don't have to stop it here because whenever the WebAudio API reaches the end of the buffer, it will stop it for us. So we save a few lines of code. Okay. What? Yay! Cool. So yeah, pretty standard. Up, let's stop. Oop. And then, what do we want? We want to drop the bass. Okay. So we're going to use the same concept as we've seen in the slides. We're going to do 2 oscillators, slightly detuned. So oscillator 1, and I can't type. Okay, cool. So we've got ourselves 2 oscillators, and we're gonna need a gain to change the envelope, so it's not boring. Create gain. And then we're gonna need a filter, because filters are cool. Okay. So this is the nodes we need. Then we need to connect everything. Filter, connect, gain, connect, sync. Connect. Gain. Oh, I've connected the gain twice. Okay, good. So we've got all that connected. The difference between the synth, the bass, and the other instruments we had is that the bass actually has notes, whereas the kick drum and the hi-hats is just, it happens or it doesn't happen. So we need to get the note, which is passed here, conveniently in the function. And we need to convert it to a Hertz value, so using the barbaric formula that I talked about earlier. So note to frec, which basically you have in every WebAudio API program ever. The same one-liner. So you set the two oscillators to the same frequency, to the same note. And you want to slightly detune, so put out of tune the second oscillator only. So they don't play exactly the same note. So by 25, see 25 out of 1,000, I think. I can't remember the unit. Yeah. Then we want the type to be a sawtooth. So sawtooth looks like a sawtooth. It's got very harsh sound, pretty aggressive, in-your-face kind of sound. And then we want the note to start at full volume and then gradually decrease, but pretty short because the pace of the notes are pretty high. So you want the note to be finished when the second one hits. So same technique. We want to put it at full volume at first, at time t, and then you want it to drop to 0 from time t, but with a short duration. And then you want to make the filter a bit more aggressive, so you change the Q value. It's something I haven't talked about because it's a bit complicated, but again, I'll have notes for you after the talk with very detailed explanations. But it sounds better, so I'm just going to put it in quickly. Up. And whenever the note hits, I want the filter to move. So the note will start, the filter will be closed, and not a lot of very high, harsh sound will pass through. And a few moments later, during the same note, the filter will open and let some treble through. So it will make a very nice dynamic sound. And this is exactly why the TB303 was very appreciated by acid techno musicians, because it was a very dynamic and quick synthesizer. Also, it was super cheap back in the day. So the frequency of the filter will start at a very low value of 400 and will quickly rise to 3,200, but pretty quickly. And then we're going to start our 2 oscillators and stop them a moment later. One second later. And if I'm not mistaken, it should make some sound. Yep. And we could do some changes. For example, we could make it so that the frequency doesn't go as high. So we can change the characteristics of the sound very easily by just changing a number. If you want to simulate, for example, an open hi-hat instead of closed hi-hat, the hi-hat sound is much longer. We can change values like that by adjusting some sounds. But yeah, really, we've written how long? So we've got starts as 100 something. Yeah, it's a bit less than 80 lines of code, and we've simulated the kick drum and the hi-hats and cheated for the clap, but it's there nonetheless, of TR-808, which is the, I think, most used drum machines ever. And with a couple more lines of code, we've simulated a pretty nice synthesizer. So that lets you have a look in how the WebAudio API is quite powerful. Of course, you can do a lot of other things with it. Instead of synthesizing sound, you can grab live source, for example, a microphone, or you can grab a network stream, or a YouTube video, or a SoundCloud track, and apply some processing. You can really go crazy. And I think that's basically it for my talk. So thanks. So if you feel like digging deeper, I've written a page. This is the link. It's on GitHub, and it's literate style in the sense that on the right you've got the code, and on the left you've got big paragraphs that explains everything that happens, and with insights into music theory, sound synthesis, a number of things. It goes really deeper. If you want to go even deeper, you just Google synth secrets, and it's a 65-article series about a super crazy nerd that reverse engineers a number of synths and tells you how it works and everything. And again, thank you. I'm Adenot on Twitter, Adenot on GitHub, and if you have anything to say, just hit me up on adenot@mozilla.com, and if you have any questions, happy to answer.
Okay, some questions. Anyone, raise your hands.
Hi. Is it possible to record to a file, like an MP3 file, directly or download while using the web audio?
Yes. So to do that, you use an object on the web. It's available in JavaScript. It's called a media recorder. And so whenever you create a media recorder, it asks you for a media stream that you can get very easily in the WebAudio API. There is a thing that is called a media stream destination. If you look in the specification, or if you browse the link in my talk, you can find pretty easily where you can get one. And then the second parameter of the media recorder is a MIME type. For example, you can say audio MPEG, and that would be an MP3, or audio Vorbis, or audio Opus, and you pass in quality parameter and everything. And this encodes in real time and gives you chunks of the data. and you can start it, stop it, slice it. You can do a number of things, and at the end you've got an MP3 or a Vorbis. It works for video as well, by the way. So if you want to encode video on the web, it's available on IE Edge 12, IE 12, Firefox, and on the last Chrome version. They just released it. So yeah, but yeah, you totally can. Yeah.
Thank you.
Next question.
Hi. Have you tried doing this procedurally?
Sorry?
Procedurally. Have you tried
Yeah.
making the music?
Yeah. Because, I mean, I also happen to have written the code, the C++ code that runs all this. So yeah, it's kind of procedural for me because I've written everything. But yeah, you can also write custom JavaScript and do it all by hand, if that's what you're asking. I'm not too sure. Oh, multiple problems. Okay. Sorry. We can talk afterwards if you want. Censor. It censored me. Oh, it works now. Oh.
Hi. I was wondering, like, you were always calling the functions in
Yeah.
creating the nodes. Could you reutilize those nodes?
You can, in some capacity. The model of the WebAudio API for nodes that create sound is a fire and forget. So you create the node, start it, and when it stops, or if it stops, if you stop it, you cannot restart it. You have to get a new one. Okay. But it's not a big problem because it's very cheap to create nodes.
Yeah, because I was worried about performance, really.
Yeah, no, you can, like more than 10,000 something nodes have been created for the symphonic orchestra thing I was talking about earlier. Okay. So it's very super cheap. If you want to reuse the nodes, you can always stick a gain node in front of it and set the volume to 0. Okay. So in this way, the sound doesn't get through. Yeah, you can, so that's for nodes that create sound. For node that doesn't create sound, that process sound, there you can reuse them. You just disconnect and connect stuff to it. And the engine, internally, when it finds that nothing is connected to it, it optimizes it away and it doesn't process it because only silence is coming into it. So.
Any more questions?
Are there any concerns about latency when using this for, say, live performances?
Yes. So when you play a video on YouTube, for example, we don't care too much about latency. We just want the audio and video to be synchronized, and we care more about saving the battery of your device. When you use the WebAudio API, we are very aggressive about the latency. So we pick the lowest latency that is available on the platform. So for example, this means that on a MacBook, you've got like 5 milliseconds or something. Well, the lowest you can go, depending on your sound card. On Windows, it's like 10 ms. On Android, it can be terrible or good, depending on your device. This is always like the biggest problem on Android. But yeah, we are extremely aggressive about latency, which means you can do really interactive things. And it's been done, in fact. That said, if your WebAudio applications doesn't care about latency and you would like to save battery instead, then you can specify it when you construct the audio context. And you say, I value more battery and CPU usage than latency, and then we switch things internally for you and let you or your users save battery. So yeah, you've got, depending on your application, you can decide.
Okay. Can you apply this programming to hardware?
What do you mean? Like to plug hardware synths with it?
Yes.
Yes. So for example, a story I have is that I have one of the little Volker synths from Korg. And the Volker is a tiny, tiny synth. And they are synchronized where you send them little clicks, audio clicks, and that gives them a tempo. So what I did is that I wrote a web page that outputs a little clicks. And so it synchronized my WebAudio API application and my analog synthesizer. So they could play together. Another way to use hardware with it is to use the Web MIDI API, which I haven't talked about, but exists. And that lets you talk to MIDI-enabled device, whether it is by USB or by old-fashioned MIDI cable, and send MIDI messages and receive MIDI messages and process everything. And yeah, so that's two ways you can control and play with synths and external hardware on the web.
Okay, thank you very much. We'll now announce the winner of this talk. Does anyone have a number?